Okay, thanks so much. Everyone hear me? Mic's working okay? Not too loud, not too quiet? I got funny shaped ears, so it was hard to attach, but I think we're okay. So I don't, sadly, have any great stories about Arizona, though I'm reasonably convinced that the next 4 or 5 days will not be without suffering. Despite ostensibly having a background in arithmetic geometry, my first time here was in fact only 2 years ago for the winter school on perfectoids, when I served as a project assistant for the lecture series on periodic Hodge theory. So I'm happy to come back this time and tell you all something about the subject of topological Hochschild homology, which a priori may have very little to do with such things, but as we'll see, in fact, is remarkably close. So the rough goals of this course are going to be the following. I'm going to start, this will be the focus of today, just by giving you some presentation of this very classical point of view on Hochschild homology and cyclic homology and the various variants thereof. And then we'll turn at some point to the topological counterparts of these theories. And along the way, although these theories have appeared in various abstract contents, the point of view that I'll be adopting throughout is how we can actually relate these things to arithmetic geometry and algebraic geometry, and how they can help us from that point of view. Okay. So today I'm going to actually jump straight in without any real introduction and tell you about the very classical theory. So this really requires nothing more than first course in homological algebra, to be honest. At times you might need to focus a little bit on whether things are chain complexes or co-chain complexes and which degrees things live in, but it honestly doesn't require more than that. So and nevertheless, I hope at the end of today to be able to give you just some little indication of how this theory can produce something interesting if I plug in something of a, let's say, of a perfectoid flavor, but that we won't then see until the very end. So let me fix for today some commutative base ring K, and then for any K algebra, we'll consider various sorts. We have this thing called the Hochschild complex. Defined explicitly as follows, so we call it HH of A over K. And so here goes. First I put a single copy of A, that's in degree 0. Then I have 2 copies of A tensored over K. Oops, that's an A. Then I have 3 copies, always tensoring over K, and so on. And the boundary maps are as follows. So the first boundary map, I've got some A0 tensor A1, and I send this, I multiply the first 2 elements, that is to say A0 and A1, and then I bring the last element round to the front, and I subtract that off. So that's minus A1, A0. Should become a little bit clearer with the next term. So I have an A0 tensor A1 tensor A2. So I multiply the first 2 to get an A0 A1 tensor A2. Then I multiply the next 2, that is to say A1 and A2, and I subtract that off. That's an A0 tensor A1 A2. And finally I bring the last term, the A2, round to the front with the right sign, A2 A0 tensor A1. And so I continue in this way, always multiplying together adjacent elements, including the last term by the first term, and I add them up in an alternating fashion. And then the Hochschild homology groups. HHn of A over K are just by definition the homology of this complex. So I hope that the definition of this complex, I think maybe everyone has to be happy with the definition of this complex, or you're going to be lost from here in. So, yes, great.
I feel like it would look more cyclically nice if it were A1, A2 tensor, A naught. Like, why is it the way that it's? Why the way that it is?
A1, A2. There is an A1, A2 tensor A naught. There's one of those right here. So it's cyclic, yeah? You've tried to find something non-cyclic, but in fact it's there. Next challenge. So I got a string of symbols, I multiply these, and 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 then I multiply these ones. Okay, so I take the homology groups of this complex, and that's super classical Hochschild homology. So here are some examples of how it looks. And at the same time, I'll throw in some basic properties. So let's start with HH0. So this, by definition, I'm just modding out A by the image of the first boundary map. That's to say I look at everything of the form AB minus BA. So that's what you'd call A modulo its commutator. But as far as I'm concerned, non-commutative rings don't exist, so this is just A. And I think basically from now on, A will be commutative. Maybe I'll write a couple of things in greater generality. So sticking with this commutative case, let's calculate HH1. Oh, so I'm allowed to point this, but I'm allowed to write on it. Okay. So for H, no, but then you can't see me, can you? So if I bring this back here. So HH1, okay, in the commutative case, we've just noticed that the first boundary map is 0. So HH1 then is just going to be this term modulo whatever I get from degree 2 elements. That is to say, it looks like A tensor Ka, and I'm just modding out by things of the form AB tensor C minus A tensor BC plus AC tensor B, where I'm allowed to exchange AC and CA because I'm commutative. That's for all A, B, and C's in my ring. And this, you see, what I've modded out by is exactly the sort of classical Leibniz rule that one uses when defining different differential forms. And so indeed this corresponds exactly to the classical module of Kähler differentials that one sees in commutative algebra by matching up, how should I write this, A dB with A tensor B. Indeed, you could essentially give this as a definition of the first module of Kähler differentials. And that's just going to be the first of many relations to differential forms that we'll see during today. So for a basic property, if we can stick all of these Hochschild homology groups together, so that is to say I form this graded object over all of the HHNs of A over K, and this will be a commutative graded K algebra, or even A algebra if A is commutative, which it always is. And that's just some formal property that if you look at the Hochschild complex, you can see that it has the structure of a differential graded K algebra. And so putting some of these things together, if you look at all of 1 to 3 together, I guess, okay, I've just written, okay, it's great, I've started the board with A as commutative, that I'm going to assume now. Then these first 3 properties imply by the universal property of differential forms. So that is to say, I form this wedge algebra on omega 1 of A over K. And by the universal property that satisfies, I get for free maps from all of the omega n's to HHN. So I don't have space to write the A over K, but you get the idea. Because I have some commutative differential graded algebra, I've got omega 1 mapping into degree 1, so when I form the wedge power, I get a map going in higher degrees as well. And these maps, these epsilon n's are sometimes called the anti-symmetrization maps, and these are biconstructions and maps which are compatible with the multiplicative structure on both sides. So that's the next relation, essentially, that we have to differential forms. And in fact, is this really okay? I'm getting a lot of feedback on the mic. Are you getting it too? Sorry, I have such a loud, booming, deep voice. The button's doing some adjustment. Better? Worse? Better? Better? I'm not getting any replies, so I assume that means that you don't hear me, which means it's worse.
It's better. I dropped the game.
Okay, I'll try to stop shouting, but it's so exciting. Okay, so we've now got some maps coming from these differential forms into Hochschild homology, and essentially the first non-trivial theorem of the subject attributed to Hochschild, Constant, and Rosenberg. This goes back to the 60s, states that if A is smooth over K, then the maps epsilon n from the omega n, so just differential forms that we know and love, to these Hochschild homology groups that maybe you're seeing for the first time, these maps are isomorphisms. And so then the philosophy that was then floating around when this subject was introduced by Kahn, Fagan, Segan, I guess one should also mention Lode-Quillen, is that even if you're not smooth, you can think of Hochschild homology, or maybe more precisely the Hochschild homology groups, as generalizations of differential forms. Even if A is not even just non-smooth, but he goes so far as to say even if it's non-commutative. So it gives you some replacement for differential forms even in the non-smooth or non-commutative context. But in fact, I'm not really going to care about that. We're really going to focus on the case of certainly commutative algebras, and lots of the time we'll be interested in studying smooth algebras. So in fact, I want to present for you, since it's the first sort of non-trivial theorem in Hochschild homology, I want to, in fact, give you a proof of this so-called Hochschild constant Rosenberg theorem, matching up differential forms and these Hochschild homology groups. So it goes as follows. So first one adopts a slightly different point of view on Hochschild homology. So to prove this HKR theorem, we adopt, let's say, a homological perspective on HH as follows. So for any, in fact, back to the case of any K algebra A, so I've got this complex that I wrote down totally explicitly, but it turns out you can think of it up to quasi-isomorphism as representing the derived tensor product of A with itself over A tensor K A op. So I tensor together two copies of A. One of them I've opt, so that I'm really looking at A bimodules. And then I can view A as both a left and a right module over this. I form the derived tensor product, and that's in fact represented by this Hochschild complex. And the proof of that is just an explicit calculation. So you even have an on-the-nose isomorphism of complexes between this Hochschild complex on the one hand and I'm going to tensor it over A tensor K A op, and I realized that I made a mistake at the very, very beginning, but no one's pointed it out. So I'm going to tensor this with, I'm going to first have a copy of A. Do I need two copies? I guess I need two copies. KA is the A tensor KA tensor over KA dot dot dot. Let me insert the hypothesis. For any flat K algebra A, that's going to implicitly be used. Otherwise, I mean, you can in fact recover a formula if you, in fact, the definition of Hochschild homology that I gave you is only really the right definition in the case in which you plug in a flat K algebra. Otherwise, you need to derive it a bit more in some sense. And if you adopted then the correct definition of Hochschild homology in the non-flat case, this formula would still be true as long as I replaced this copy of A tensor A op on the bottom by the derived tensor product. But then it really looks like a terrible formula. I mean, you've got A derived tensor or A over A derived tensor A. But it makes sense. I mean, then the bottom A derived tensor A becomes some simplicial ring, and you think of everything, in fact, in the world of simplicial rings, and you form your derived tensor products there. But we don't need to do that. I make myself flat so I can forget about some derived tensor on the bottom. So I form some new complex. This would be called the bar complex. Let's say B. In fact, there's no point in introducing a name for it because I'm not going to use it again. And what's important is it's going to be a certain complex. I'll tell you a little bit about the differentials in a second. It's a resolution of A by flat A tensor A op modules. Okay, here we go. Let me explain what's going on now. So I write something down here. Let me cover this up so you don't need to look at it. I write something down that looks a bit like the Hochschild complex, except I start with A tensor A instead of A. And I sort of write down the obvious boundary maps in which I don't multiply the last element by the first element. So I just multiply all possible adjacent elements with alternating terms. Then it's a classical result in homological algebra that this, because A is a unital algebra, this complex is in fact exact except at degree 0, where you can see it resolves A, because if I send A tensor A to A by the multiplication map, then the image of this boundary map precisely describes the kernel of multiplication. So this complex then, this so-called bar complex, becomes a resolution of A by A tensor A modules, and under this flatness assumption, then all the terms appearing here are flat as A tensor A modules, and when I then base change along A tensor A op down to A, well, it exactly has the effect of introducing this multiplication of the final term by the first term, which one sees in the definition of the Hochschild complex. So you literally get on the nose an identification between these two complexes, and the thing on the right-hand side is computing this derived tensor product that one cares about. So one could then ask, why do we not just, why did I go through this process of writing down some explicit complex to torment you and not just present you with this very, very beautiful, perhaps, this very beautiful formula for what we're going to study? And the reason is essentially that when we then pass the cyclic homology, we're really going to use, at least from the sort of naive point of view that we adopt today, we're really going to use the explicit presentation that we give on the left side. Yes? Well, that's right. Okay, so you've got an A and you've got an A op. Yeah, so the A acts on the left term and the A op acts on the right term. And so then when you then mod out via the multiplication map to A, it exactly has this, it identifies the left action and the right action, which introduces this cyclic. And so I guess, okay, I can say now a word about this proof of this HKR theorem. I hope that's, yeah, so the HKR is still up, so we've got to check that these maps between differential forms and the Hochschild homology groups won't these always be isomorphisms. So now, so A is again now a smooth K algebra, and we must show, let me rewrite the problem. I just need to show that this graded algebra of all Hochschild homology groups is the exterior algebra on its degree 1 elements. So as that, I'm trying to prove that in general HHN looks like omega n, which is by definition the wedge n of omega 1, but we already know that HH1 looks like omega 1. So this is then just a reformulation of the isomorphism that we want to check. And so now becomes a problem which is now entirely internal to Hochschild homology. And this is, now I can just cheat and say that something is well known. This is well known for the graded algebra in which I look at tors. Let's look at some tor algebra that looks like this when I have some surjection whose kernel is locally generated by a regular sequence. So if you have some surjection of commutative rings and the kernel is locally generated by a regular sequence, or let's say in fact it's generated by a regular sequence, then you can calculate this sort of Tor using some explicit Koszul complex, and you'll just read off from that in fact the Tor groups are just the wedge algebra generated by the Tor one. So as I say, some reasonably classical piece of homological algebra that just follows from this explicit Koszul complex calculation. And so what's such a case when a surjection of rings has a kernel which is locally generated by a regular sequence? Well, for example, A tensor K to A, this is the multiplication map, since K to A is smooth. Again, that's some classical piece of homological algebra. You might as well imagine, I mean, at least locally, A is basically going to look like a polynomial algebra. I mean, up to localizing it and maybe looking at some little Latal extension, it'll look like some polynomial algebra. And so you've got, like, say, K polynomial variable T, tensor K polynomial variable T, mapping by multiplication down to K of T, and then the kernel of this will just be generated by T tensor 1 minus 1 tensor T. That's your regular sequence, cutting out the kernel of multiplication. And that's true in general. So because A is a smooth K algebra, the kernel of multiplication will be cut out by some regular sequence. But then we're done because we can apply the previous lemma. We know that the Hochschild homology groups are exactly calculating the Tor groups. I should probably have explicitly written that on the previous slide. So corollary is that the Hochschild homology groups look like, just by passing to homology groups, they just look like these Tor groups. Okay. And that, I think, is actually all I want to say about Hochschild homology. And to some extent, that's the end of the story, at least if you're only interested in the case of commutative algebras. I mean, you write down this explicit complex, and you check that in the case of a smooth algebra, it recovers for you differential forms. And I should emphasize that something interesting is happening there. I mean, we've written down it's kind of counterintuitive. I mean, normally when you look at differential forms, you use them to form the de Rham cochain complex. And now what we're saying is we've written down some chain complex whose homology groups are giving you the terms which appear in the de Rham cochain complex. And the reason for this, what we're going to see in a moment, is somehow exactly this theory of cyclic homology. It explains what's going on and explains that this Hochschild complex is some enrichment of the Durand complex that lifts it to a, well, I'm trying to say some nonsense, I'm not sure if it's true, I mean lifts it to some sort of higher homological level. Anyway, let's make precise statements instead of these quasi-statements. So let me go ahead now and tell you what's going on in the world of cyclic homology. This is all getting. Okay, so next is very classical cyclic homology. So let's return to this complex that we wrote down and look at a little bit of extra structure that it has. So we had this A, we had this A tensor A, we had this A tensor A, and so on. And all the tensors are over K. I'll try not to be sloppy. Let me include them. Okay, so this first thing, here's some good structure. It is acted on by Z mod 1. Oh, yeah. The next term, finite simple group of order 2. Okay, Z mod 3. Okay, you see the pattern. In general, okay, you think you see the pattern, but then there's going to be some terrible piece of terminology, some terrible piece of notation appearing. So in general, I've got Z mod n plus 1 acting on A tensor n plus 1, and I don't do this. Okay, let me explain, this is not my fault. I mean, this is someone else's fault. But the generator of Z mod n plus 1 is denoted by T sub n. There's a reason for it. Okay, the reason for it, I mean, okay, a little bit more seriously, I mean, this copy of Z mod 2, for example, is acting on the terms in homological degree 1. And so in general, when you try to abstract what's going on, you're going to have some gadget sitting in homological degree n, and that's what's acted on by Tn, but it's an operator of order n plus 1. So it's not completely insane. So how does this act? I mean, just to eliminate any fears about whether I move things to the right or the left. Okay, I take my symbol like this, and my generator will act by okay, pretend there's another tensor symbol there, I'm sorry. I just shift everything to the right. Okay, so we've got this little bit of extra structure, and so let me introduce then. This is really the very classical approach to how Kohn then got to cyclic homology. You use these actions to introduce some other operators, which we'll see perhaps more intrinsic or more highbrow interpretations of later in the lecture course. But for the moment, let me just adopt the very explicit formulae. So one introduces some map called the norm. So this will be the sum, and I've got to always check the signs and the n's or the n plus 1's, minus 1 to the n Tn, and I take the alternating sum of these, and that will go from A tensor n plus 1 to A tensor n plus 1. So in fact what I do is I twist my action, possibly by a sign of minus 1, depending on whether I'm in even or odd degree. And then I really do take the norm, that is to say, add up the actions of all elements of the group. And then, so that's, as I say, that's the norm. And then the next map in the story is the extra degeneracy, as if it wasn't already degenerate enough, S. So this will go from A tensor n to A tensor n plus 1, in which I just take some A0, blah, blah, AN, insert some tensors, and I stick a 1 in front. So let me explain the reason for the name. So I wrote down the Hochschild complex as a complex, but in fact it's really the complex associated to some simplicial K module. So simplicial K module means I've got these face maps and these degeneracy maps, I always forget which ones go up and which ones go down. So the boundary map is then the alternating sum of the ones going down. You don't really need the ones going up. But so the degeneracy maps going up are given by inserting ones at various places in the tensor symbols. Except that this one doesn't actually appear. So that's why it's called the extra degeneracy. You could allow to insert ones at any other places in the degeneracy maps, and that's kind of an extra one that we now write down. And then finally, this is the most important. In fact, the definition is not important. Cons operator B. So this is going to go from A tensor n. And I go first to A tensor n, then I go to A tensor n plus 1, and then we'll finally end up in A tensor n plus 1. So overall, I'm going to increase the degrees by 1. So I do it as follows. First, I apply the norm, then I apply the extra degeneracy, and then I apply identity minus twisted action. So minus 1 to the n t sub n. So here's what you're supposed to check. If I do this twice, I get 0, and it's compatible. Okay, so I forgot a piece of terminology. B, okay, where B is the boundary map in the Hochschild homology complex. So that's again a piece of classical notation that the initial boundary maps I wrote down when defining the Hochschild homology complex are usually denoted by a little b. So I wanted to give you the formulae just to show you that the formulae look terrible. I mean, to be honest, they're pretty explicit. And what one then checks, and this is really all that one cares about, is that this big B twice is equal to 0, and that it's compatible with the existing boundary map on the Hochschild complex. So to summarize, we started with this Hochschild complex, which was a chain complex under little b, and I've now written down a map in the other direction, big B, which gives it the structure of a cochain complex, and is compatible with the existing chain complex structure in the sense that this relation holds. And this structure of simultaneously being a chain complex and a cochain complex in a compatible fashion is what is classically known as a mixed complex, or an algebraic S1 complex, where this S1 is the circle, which will play a role when we start to adopt a more highbrow point of view on these constructions. But instead of thinking of it as simultaneously a chain complex and a cochain complex in a compatible way, you should stick to thinking of it as a chain complex. So you should keep thinking about HH, and you should think of this map B as being a map from the Hochschild complex to itself, but of degree -1. So this -1 means I think it's homological shift notation, but for a chain complex with a -1, that means I shift it to the left. That's what I want to do. So I have everyone agree? We can vote on whether it's left or right, but I think it's left. So I take my Hochschild complex, I shift it one to the no, shift it to the left. Yeah, shift to the left, great. And then I have a map from the complex to itself, but taking this shift into account. So the idea of this operator, I was going to say lift, but let me really say this refines the de Rham differential. So in the following sense, so the fact that B is compatible with little b means that I suddenly get an induced map on the Hochschild homology groups. Well, similarly, I've got my de Rham differential on differential forms. We had these maps coming in which at least in the commutative case, which in general don't need to be isomorphisms, but they are in the smooth case. And that should be an n plus 1. And the statement is that this diagram commutes. So not only are we saying that this Hochschild complex, that its homology recovers the terms in the de Rham complex, we're even saying that the de Rham differential, which appears in the de Rham complex, lifts to this complex. Some of the entire structure of the de Rham complex has been lifted in some homological fashion. And so we're now going to sort of pretend we were trying to construct de Rham cohomology, but we're going to do it to the Hochschild complex. So here's the definition of cyclic homology and all of its variants. So again, I'll give you one of the classical explicit definitions, and we'll see fancier, more highbrow approaches later in the course. So I'm going to write down a bunch of copies of the Hochschild complex. So that goes off like this. So it's a periodic family of copies of the Hochschild complex in which I shift them a little bit. Okay, these are all then Hochschild complex, whereas I say the boundary map is traditionally denoted by a little b. And then I can connect them with this operator Judicon, but I mean, axiomatically speaking, all that we're using is the fact that I have compatible structure of chain complex and cochain complex. Well, they're compatible. And that lets me write down this anti-commuting double complex. And then one defines the periodic, I should give it its name, the so-called periodic cyclic homology of A over K. Again, any K algebra A is defined to be the totalization of this double complex. So that's in fact, it's some chain complex sitting both infinitely in positive and negative degrees. And when you think about how this works, I'm adding things up here, adding things up here, adding things up here, adding things up here, and it goes infinitely in both homological and cohomological directions. And then HC of A on K, so this is classical cyclic homology. That's defined to be the totalization of, I've got some colors, let's use them. Okay, X is, I didn't tell you. So let's decide that this guy here is in bi degree 0, 0. So that's the origin. And then I'm infinitely spreading out. And then I can just look at what's going on this right half plane. So as I say, I kill all of that. You pretend that I only drew a first quadrant bicomplex, and I define HC to be the totalization of that. And then what's left, I can also totalize, better change color, the x less than or equal to 0 part. So again, I pretend that I hadn't drawn anything in the right half plane, so now I just have a left half plane bicomplex. I totalize that, and I get the so-called negative cyclic homology. Cyclic. I was going to write it in a French way. Cyclic homology. So there we go. So let's now just write down some really, here's some really coarse information to start with. So as I mentioned, HP, this is given by totalizing something, and it's going to sit it's going to sit infinitely in both homological and cohomological degrees. It extends infinitely in both directions. Cyclic homology, okay, there I totalized something which was in the first quadrant, so it will in fact just be sitting in positive degrees. And negative cyclic homology, it will again be going off in both infinitely positive and negative degrees. So let's write down a few, just basic structural properties of these things that you can read off straight from the definition. And that will in fact allow you to forget this nasty spectral sequence for the most part. Let me start dropping the A over K. It gets a bit heavier. Let me just write down HH, HC, and so on. Okay, sorry. Okay, my better point. So remember the cyclic homology was given by forgetting everything on the left side. So just focus on what's going on in this right half quadrant. Well, then obviously, if I also cut off a little bit more, well, I get the same as I started with. It's shifted by degree 1, 1. And what did I chop off when I chopped that little piece off? I chopped off exactly a copy of the Hochschild complex. So in other words, cyclic homology maps onto cyclic homology shifted by a bit, and what I lost was Hochschild homology. So I've got a short exact sequence of complexes, like so. And similarly, if I take the negative theory, I shift it a bit, I include it back into the negative theory, I'll get a short exact sequence like that. So let's do that one again. Let's suppose I've forgotten about everything on the right half plane, so I'm just looking at what's going on this left half plane. Well, then if I chopped off this central column, I'd be left with a copy of what I started with, but shifted by a little bit. So that's just telling me that if I if I map onto this column, then in fact the information I've lost is just a copy of what I started with, but shifted by a little bit. And the most important of these, this is what will definitely appear when we turn to the topological theory later, is the so-called norm sequence, which makes the obvious statement that the totalization of the whole diagram is sitting in between the totalization of the stuff on the left and the totalization of the stuff on the right. And maybe finally one more. Okay, so to totalize the whole big diagram, I could instead chop it off here, totalize, then chop it off a little bit more to the left and totalize, then chop it off a little bit more to the left and totalize, and then take the inverse limit over all of these. And that would give me the totalization of the whole thing. And that amounts to the statement that I can think of the totalization of the whole thing, namely this HP, as being the inverse limit over various copies of the totalization to the right, that is to say, cyclic homologies, along these periodicity maps. And that's where the name periodic cyclic homology comes from. I mean, it tells me that we could also just read this off from the original description, that periodic cyclic homology really is two periodic. It has this operator which induces an equivalence between itself and itself shifted by 2. That in any case, as I say, is obvious from the diagram. I mean, it has this 1-1 symmetry. And so in particular, I mean, looking at homology groups, these are also going to be two periodic. So the nth periodic homology group question. Yes. I thought there was some, yes. Ah, great, you win a prize, because no one else asked. Product. Exactly, yes. This is important. This is important. Indeed, when you have an unbounded, when you have a complex which is unbounded going up in this direction, you care whether you're taking the direct sums of all the terms that are appearing or the direct product of all the terms which are appearing. And in order to have this final formula, that I can view it as the inverse limit of what I get if I truncate at any fixed stage, then I would definitely have to be taking the products. Yes. Ah, does that, sorry, I thought that was going to, the, up here, second line. No, should be -2. Thank you. That one I think is actually okay. Let me come back here. And so I've written down all these random sequences. I mean, the point of them is just that, and I'm going to give you a manifestation of this in a moment, is that coarse information about HH gives coarse information, A gives coarse information about all of these HP, HC minus, and HC in a sort of natural fashion. But of course, I mean, that's somehow clear from this description as a totalization. And if you know something about all of the columns of some anti-commuting bicomplex, then you can say something about the totalization. But I want to give you, to finish, one concrete consequence of this. We're going to use these definitions very formally to build some interesting thing. So here goes. So here's an example of that philosophy that we'll come back to and study in more detail when we start looking at characteristic P and some p-adic phenomena. So assume that these Hochschild homology groups of my K algebra A vanish in all odd degrees. E.g., and this is just to tantalize you a little bit, to wake you up, if A is perfectoidish. I don't want to make too precise statement for the moment. If A is, that's not the latest definition in the subject, don't worry. But if A, we'll see if A is coming from something which is kind of perfect or kind of perfectoid, then we'll see phenomena of this happening, where the Hochschild homology is really supported in even degree, and then just using these formal definitions and some of these formal properties, well, let's construct something interesting. So let's have an informal statement. The 0th periodic cyclic homology group is a complete filtered ring which encodes a lot of the above data. Okay, let's make this, it's really imprecise, so let's do a little bit better. More precisely, so HP0. So firstly, it follows, I've kind of swept over multiplicative structures of these constructions, because then you have to get your hands dirty. Well, either you adopt a better point of view, and that's what will eventually happen, or you have to get your hands dirty with differential graded algebra structure, which I didn't really want to do. In particular, the graded direct sum of all of the HP homology groups, this will form a graded algebra, and in particular its HP0 is some ring. In fact, it's some K algebra. So this HP0, let's say, is a ring with filtration by ideals. Let's get this right. Let me call these fil I HP0 of A over K And what are these? I'm going to just apply this periodicity operator some number of times to hc minus of 2n of a over k, so for n bigger than or equal to 0, such that, and I just need maybe 2 minutes, such that hp0 of a over k modulo these fill i's, these will recover for us hc of 2n minus 2 of a over k, and so I have some filtration. I can look at the graded pieces, and these graded pieces will look like the Hochschild homologies. Oh, I'm moving between n's and i's. N equals I, okay? There's an n, there's an n, there's an n, there's a 2n of a over k. Okay, so let me now explain what's going on. We just impose as an assumption that the odd Hochschild homologies vanish. Well, then we just come back to our, well, we could either look then at the spectral sequence that results from totalizing this gadget. When we go to the next page of the spectral sequence, everything will be sitting in even degree. And so the same will be true for HP, HC, and HC minus. Alternatively, we could look at this short exact sequence here. The HH is supported in odd degree. So if you write down the long exact sequence to this, well, you'll deduce that there's no HC1. And then using this, in fact, you'll deduce that there's no HC3 even, I suppose. And then by chasing the long exact sequence backwards, you'll gradually deduce that there's no odd HCs. And then let's see if you've got no odd HCs. What's the easiest way to then get it? Okay, now the easiest way is really just to read it off the spectral sequence associated with totalizing this thing. It'll tell you that the periodic cyclic homology, the negative cyclic homology, and the cyclic homology are all supported in even degrees as well. And then that tells you that all of these long exact sequences, when we pass to homology, they all break into short exact sequences, because there's nothing in odd degree to mess things up. So in particular, the map from the HC minus theory to HP theory, this is injective on all homologies. So I can take something sitting in HC minus of 2n, I can apply lots of periodicity maps, and this injects into HP0, and it sits inside it as some ideal. And then the quotient you'll read off from this sequence will be some copy of cyclic homology. And the graded pieces you'll read off from the second short exact sequence, that the difference between two negative cyclic homologies you get as a copy of Hochschild homology. So the conclusion is essentially that a large amount of the data of the periodic cyclic homology, the negative cyclic homology, and the cyclic homology, they're all encoded in the data of this HP0 as long as we equip it with this filtration, and as long as we keep track then of this filtration. And so the idea will be later in the course that we'll stick in these perfect toy dish things into the construction, and the output will be some filtered ring which encodes a lot of information about all this gadget. And what will that filtered ring be? It'll either be something that we know, though it'll be hard to check that it identifies with the thing that we know, or it will be something completely new. But then you have to wait and see. So I finished there. Thanks very much.
Questions?
So these perfectoid-ish rings, if you use the HKR theorem here, it wouldn't work, right? You wouldn't.
It won't be smooth. I mean, these things are very non-smooth, yeah.
So is it something like a P completion of something that's smooth?
No. It'll be something really, really very non-smooth.
Okay.
Totally non-smooth. They won't have any differential forms, in fact. Like the omega n's of these rings, they'll all vanish. So we won't see any information coming from differential forms. All the information will be encoded elsewhere.
Great, thanks.
Other questions?
So this periodicity property for HP looks a little bit like the periodicity of group cohomology for a cyclic group. Is there some way to actually sort of represent group cohomology for a cyclic group in this setup?
Thank you. That will So if you stick in a group algebra of an arbitrary group, then the let me say commutative group. Let me say abelian group.
Well, we're talking, I was asking about cyclic.
Great. Can I do Z mod 1? Is that...
Well,
now if you stick in any, let's say any abelian group, then the Hochschild homologies will give you the group cohomology, the group homology of the group. Yes. And in fact, the HP in that case, what happens in that case is that the differential big B is in some sense homotopically trivial. So you can essentially pretend that all these B's were 0. And then HP will just decompose into an infinite product of all of the group homologies. And the periodicity map will indeed then just be shifting these according to periodicity of group homology.
Okay, maybe we should take a break. So leave further questions for the break, and we'll resume again at 3:45.